Recording's going. As always, if you have any questions or you're stuck on something, just let me know. So, today we're going over prefix sum. So essentially what that is it's it's this idea of like keeping the ongoing sum up to like a certain index in the array. So like for example, I'll just construct a prefix sum array later, but essentially what you kind of want to use it for is, let's say that you need to get the sum on a range. So like if we want the sum from like 1 to 5, we need to add up index 1, 2, 3, 4, and 5, right? So the easiest way to do this is by writing a for loop, starting at here and going to here. But as like you might figure, there's a lot of occasions where sometimes we need to constantly get the range on these sums. So it's not always like going to be like efficient to just recalculate from left to right each time. So what we can extend, or what we can instead do is we can construct a prefix sum array so that we can get the sum in just one operation each time, instead of writing this for loop that goes from one index to another. So the way that we can visualize it first is, like I mentioned, the prefix sum is the sum from the beginning stopping at a given point. So the prefix sum array, so I'll just call this P. Um, for index 0 will be 4. The one at index 1 will be the first two elements, so 4 plus 3, so 7. The prefix sum up to index 2 will be the first three elements combined, so 9. And then up to 3 we have to add the 7, so we get 16. And then 4, it's adding everything together, so we can just take this and add 5 to it, so 21. And then for the last one, we have 27. So this is our corresponding prefix sum array for this array up here. So now if we want to get the sum on a range, instead of looping from like left to right, we can instead think of getting the sum on a range as taking the sum from the beginning to this index and then subtracting the part that we don't want. So what I mean by this is, let's say we get the sum from 2 to 4, right? So what we can do is we can get the sum from the beginning all the way up until this index right here, and we know that that's the one in this cell right here, right? So 21 gives us the sum from the beginning all the way until here. But the thing is, we don't want the sum from 0 to 4, we want it from 2 to 4. So what we're going to do is we're going to subtract the part that we don't want, which is the first and second element, right? So instead of looping from left to right, what we can instead do is generalizing this to be the left endpoint as L and this as the right point as R. We can get our sum by um taking P of R and then subtracting P of L minus 1. And the way the subtracting L minus 1 part works, right, is if we want the sum from 2 to 4, we should subtract the sum that's on the left of our starting point, because we don't want to include anything of this, right, if we want just 2 to 4. So we can take everything from here and then just subtract everything at the beginning. And now we can get our sum in just getting this from the array, getting this from the array, and then subtracting them instead of having to loop through it each time, right? So the advantages behind this in more like specific time complexity cases, I guess, is in C++ you can only do 10 to the 8th operations in a second. So if you have an array of size 10 to the 5th, for example, um you can only like get the sum on like this range so many times before it times out. So if your array is very big and you constantly have to check the sum within ranges, this will allow your program to actually run in time, because you're not looping each time. Like, you've made this and then it will take like literally like a millisecond to get any sum you want. It doesn't matter which one it is. I drew like 2 to 4, but we can generalize it to anything else, right? Let's say we want the sum from 0 to 5. This one's easy. We just take the element in this cell right here, because by definition, this cell is the sum from the left to the right. But if I do another example, let's say we want the sum from uh, 3 to 5. So that should be so the sum from 3 to 5 is 7 plus 5 plus 6, or 18. But what we can instead do is get the sum from the beginning to 5. So we take the 27 and we subtract the part we don't want. The part that we don't want is 0 through 2. So we need to subtract these three elements, which is found by this index right here, right? So what we can do is we can do 27 minus 9, which is also 18. So in both cases it works. This way is just faster. Are we all good?
Good. Yep.
Cool. So if we're all good on that, I'll show us another technique. This is used for like updating values inside of an array. So let's say that you have to like increment everything on a range by a certain amount. Like let me make some random array first. So and let's say that everything is pre-initialized to zeros. So so what happens is let's say that we have a problem where like you have to, spoiler alert, this problem is straight up just one of the ones on Cody that you'll have to solve, where your array like starts off at like some given value, or maybe it starts off at all zeros, and you have a bunch of operations to perform, and you have to print what the array is at the ends. And the operation that you're given is like let's say increment the sum from 1 to 3 by 4. So check what's from 1 to 3, increment them all by 4. So now this becomes 4, this becomes 4, and this becomes 4. And let's say you just get another operation, like increment everything from 3 to 4, like by 2. So you take this, increment it by 2, this, increment it by 2. So like the other problem, we could simply process all of these queries by looping from left to right and then incrementing by this amount. But once again, like this solution is gonna time out. Like if we have too many elements in our array. So we can use the concept of prefix sum to speed this type of problem up as well. So what we can do is what happens if let me reset this array. So I'll just set everything to 0. So let's say that we want to increment everything from 2 to 3 by 3. So what happens if I come to index 3 and I set this to 3, and then I take the prefix sum of this array? Well, this index is 0, this index is 0, this index is 3, this index is 3, this index is 3. The reason these two are also 3 is because I want the sum from the beginning to this point. So 0 plus 0 plus 3 is 3, 0 plus 0 plus 3 plus 0 is still 3, and then so on. So what has this essentially done? Well, we know that if I increment the start point by 3, then everything after it also becomes incremented by 3, right? So this almost gives us what we want, because we know if we take the prefix sum array, we have 0, 0, 3, 3, 3. But in reality, like what should this do? In reality, this should be like 0, 1, 2, 3, 4. In reality, we want it to be 3, 3, right? And we don't want this part to be a 3. But like with our prefix sum trick, this is set to 3, right? So how can we fix this? What we end up doing is we end up just subtracting this index after our endpoint to make sure that it doesn't influence anything past what we want it to, right? So for example, if we want to increment everything from 2 to 3 by 3, and I know that adding a 3 to our start point will add every element after 3 by this amount, then I can just subtract 3 after our endpoint. So what I should do is I should come to 4, that comes after 3, and then I should subtract 3 from it. And now what happens if I take the prefix sum of this? Well, these 4 elements stay the same, but this one is the sum from, it's the sum of the whole array, and this will be 0. And you'll notice that now this matches this below, right? So what we can like do instead of looping from left to right and incrementing like in a for loop by this number, we can take our starting point and increment it by that amount, then go one after our endpoint and subtract that amount. And then what we can do is we can construct our prefix sum array, and will be that will be the array that we actually want. Like had we like naively like written it as a for loop. So if we want to, I don't know, like see an example of this, I'll just give you like, I don't know, some example ones. So let's say increment 2 to 3 by 2, 1 to 3 by 4, and then let's go with 3 to 4 by 7. So let's first like do it naively and see what we should get. So increment 2 to 3 by 2. So we get 2 here, 2 here, 1 to 3 by 4. So these all should go up by 4. So add 4 to this one. This becomes 6. This becomes 6. And then the last query is 3 to 4 by 7. So I add 7 to this. I get 13. And then to this, I get 7. So now let's do it the faster way. So I'll set these all to 0, right? So for this one, right, I want to add 2 at my starting point, and I want to subtract 2 after my endpoint. So my endpoint is 3, so I add 1 to it, and I subtract 2 over here. Now I want to add 4 at my start point, which is 1, so I'm going to add 4 over here, and I need to subtract 4 after my endpoint. So I need to subtract 4 from here, so this will now be minus 6. Now increment everything from 3 to 4 by 7, so I come to 3, I add 7 to this, and then I go after 4 and subtract 7. This is technically like index 5, so like we don't really care about like printing this index. So like technically I would subtract 7 from here, but like since it's not within the size of our array, you can basically say that we like ignore it. So now let's construct the prefix sum for this array. So the sum up to this first point is just still 0. The sum of the first 2 elements is 4. First 3 elements is 6. First 4 elements is 13. And then the whole thing is 7. And these match, right? So the technique works. So why is this faster? Well, let's say once again that you have a really big array. Let's say like, I don't know, it has 1,000 elements. And instead of just changing a few elements, you had to update like everything to like 1,000 by 3. Well, this loop would take 1,000 operations, but this technique still only takes 2, right? Because you're only adding at this index and then you're adding at or subtracting at this index. And then at the end, you have to loop from left to right, but you're only doing that one time, which means that this top one will have a complexity of O of n to construct this array, whereas this one can take in worst case n squared. So if you want to make operations, this takes, let's say your n, or the size of your array, is equal to 10 to the 5th. 10 to the 5th plugged into this is just 10 to the 5th because you just plug the n right in. So if you can do 10 to the 8th operations in 1 second, this should take 1 over 1,000 seconds to complete, which is a millisecond. Yeah, so this would just take a millisecond to run, whereas this, you plug into 10 to the 5th into here, you get 10 to the 10th operations. I said you can do 10 to the 8th operations in 1 second, so this will take 100 seconds. So this runs 10,000 times faster, right? And if we make the array even bigger, we simply can't even like compute this in like enough time, like not only like to solve a problem, but like realistically, like what if this takes minutes or hours on bigger inputs. So that's why we really need this. Are we all good on this like trick to kind of like update an array?
Yep.
And if you want an application of like what you actually use this for, let's say the most common problem is like, let's say like you have a bunch of lifeguards that work like a certain shift, and you want to know how many lifeguards you can fire and still like have the a lifeguard for every hour that the pool is open, what you can do is, let's say like lifeguard 1 works from like 1 o'clock to 5 o'clock, another one works from 3 to 6, another one works from like 5 to 8 or something. What you can do is you can increment this all by 1. So you can say, okay, there's one extra lifeguard from here to here. There's another lifeguard from 3 to 6, another lifeguard from here to here. And then what you can do is you construct your prefix sum array to see how many lifeguards work at each time, and you would do it way faster, and you would do it here. And then like you could like remove lifeguards and check like, is the sum of the array still greater than 0, which means that a lifeguard would be working at each hour. So that would be an application. So in a way, kind of like scheduling like the minimum amount of people needed to like do something, or seeing like what you could remove. So that's kind of like a problem that I've seen use this range trick for. So this last problem, I'll just give you the solution. It's very hard, but I'll give you the solution because it can give you some intuition into the type of problems that you might want to use prefix sums for. So so let's say that you have a problem where you have a bunch of ones and zeros. So I'm just ripping this right off of binarysearch.com. So we have this array. These are just ones and zeros, so there's no like 10 here or something like that. So what you want to do is you want to find the longest like substring of ones if you're allowed to change k zeros into ones. So for the sake of this problem, k will be equal to 2. So what this means is you want to make as long of a sequence of ones as you can, and you're allowed to change 2 of the zeros to ones. So let me make a really bad solution here. So let's say I change this 0 to a 1 and this 0 to a 1. So those are the only two like that I'm allowed to do. The longest string of consecutive ones is 3, because this forms a segment of 3, and this forms a segment of 3. Now, a more intelligent way that we could go about making the solution is I want to change both of these to ones, right? And then now my answer is 6, because I have these 6 back-to-back ones. So at first glance, you might think that this is solvable with greedy. Um, in fact, I am not certain that it is. I don't think it is. Yeah, it doesn't look like it is. So so like there's a lot of things you might come up with, like for example, like I don't know, fill in the smallest gaps first or something. But it's a pretty hard implementation to know like which zero should I fill in order to get the largest sequence of ones. But what we can do is we can first construct a prefix sum of all of these ones, right? So if I do that real quick, I'm not gonna draw like the box, but like you can just pretend this is an array. So the prefix sum up to this index is 1, up to this index is 2, 3, 3, 3, 4, and 0. And how does this help us? Well, what happens is we can try every length and then see if there is some uh segment of that length that that is all ones. So what I mean by that is let's say like can we get 3 ones in a row, right? So I would check every segment of length 3 and see if their sum plus k is at least the length of the segment. So for example, actually we'll do 4. So let's say, are there 4 consecutive ones in this array that I can get? So I would have to check these 4, these 4, these 4, and these 4. So all of those. So what happens is if I want to know if I can get 4 ones in a row on this first segment right here, like this top one right here, I need to see what the sum on this segment is, and then see that if I add 2 to it, is it at least 4. And the reason for that is like if I get the sum on this first segment, like this one right here, I know that there's 3 ones, right? So if I'm allowed to fill in 2 zeros to ones, I know like I can get like 5 ones, which isn't possible because there's not 2 zeros. But like we know that there's less zeros than like what we're allowed to fill in, so it's sufficient to give us 4 ones. Likewise with the next segment, let's say we take the second lowest segment, so now this one. Um, I need to see how many ones are in the segment. We can visually see that there's two of them, right? So if I'm allowed to change two zeros to ones, then I can get 2 plus 2 ones, which is equal to 4. So I know that this segment also can get me 4 ones in a row. So the problem now stems from like doesn't this still take too long? Um and it does, because if you try every length from 1 to n, uh, each length you have to stop at every index. So if I want to check all of the ones of length 3, for example, or 4, so if I want to see all the segments of length 4, I had to check this one, this one, this one, this one, and there are at most n of those segments, right? So checking the sum of all of those will take O of n time for each of these 1 to n. So the total time complexity is n squared. Does that make sense so far? Are you good
Yes.
on it, Paul? Okay, so the time complexity of this is n squared. So in the case where there's 10 to the fifth elements, which this is like a real interview problem on binary search, we need like something faster. So what we can observe is that technically the longest length of ones that we can get in a row is a monotonic function. And what I mean by that is if we know that we can get 4 in a row, then we should also know that we can get 1, 2, and 3 in a row, right? And if we cannot get 5 in a row, from this problem we can get 5 in a row, but let's say like we cannot get 5 in a row, then we can't get anything greater than 5, right? So like there's no point checking these. So what we can do is we can binary search for the length of the string that works. So what you're gonna do is you're gonna try every length from 1 to n. You're gonna so you're gonna set your left equal to like length 1. I'll capitalize that. So L equals 1, R equals n. And you're gonna binary search. You're gonna choose your midpoint. So mid is equal to like n over 2 or something. And now you're gonna check if this midpoint works or not. And if it doesn't, then you know you have to try a smaller length to see if you have it right. And if it does work, then you should go for a bigger length to see if it does work. So that's how it works. And now the time complexity, since a binary search is logarithmic, this binary search part will take O of log n time, and then this getting each sum for all of the segments will still take you O of n time, but this will take n log n in total, which is sufficient to run this in time. I think n log n of 10 to the fifth is like I don't know, like 2 times 10 to the like sixth or something like that. So this will easily run in time to pass the problem. Are we all good on this?
Yep.
Okay. Well, if we have no questions, give the problems a shot. Call me over if you have trouble as always, and we'll do solutions at 3:20.
Is that last problem on Cody?
It's not. It's on binary search. I'll link it for you. Okay, I'm gonna stop the recording so we can